Hello everyone, welcome to lecture 4 of module 2 which is on SRAMs. The disclaimers remain the same.
The last lecture we were discussing the read and write operation in SRAM cells and why there is this read and write conflict. So another way of looking at this SRAM cell is something like this. So you have this CBL, then you have this CBL bar, which are basically coming because of the line resistances, the parasitic CGTs of all these SRAM access transistors, and also the input capacitance of your pre-charge circuitry and your sense amplifiers. So all this is contributing to your CBL bar and CBL. Then let us represent this as inverter 1. Let us represent this as inverter 2. This node is Q. We were discussing the case where Q was equals to 1 and Q bar was equals to 0. Now let us look at the read process. How we can represent this SRAM cell in terms of the cross-coupled pair that we were discussing. Let us look at that. So SRAM cell basically looks like this. So we have this access transistor M5. Then we have this inverter 1, right? Then we also have this inverter 2. And then we have this access transistor M6. These are connected to BL, these are connected to word line. This is BL bar and this is BL. This was Q, this was Q bar. And for our case, we assume that Q is equals to 1. It's at logic 1 and Q bar is at logic 0. Okay, now during read operation, what happens is we pre-charge this bit line and bit line bar to VDD. So we have VDD over here, we have VDD over here. And then what happens is, just because this node is VDD and this node is 0, this VQ bar, actually this access transistor tries to pull this VQ bar up, while the NMOS of what? The NMOS of this inverter 1. So NMOS of inverter 1 tries to pull VQ bar down. So basically the effective voltage at VQ bar is kind of the result of the tug of war competition between M5 and the NMOS of inverter 1. So that is what happens in your read operation. So instead of being at 0, so ideally we want our VQ bar to be 0, but instead of being at 0, just because this M5 tries to charge it to some potential which is like more than 0, what happens is your potential of VQ bar increases as compared to 0. So let us represent this as VQ bar is greater than 0, and let's call the magnitude of VQ bar during read as Vx. Now, what we want during read is the state of our bistable element, that is your Q equals to 1 and Q bar equals to 0, should not be flipped. So for that, what we want is, if that is the case that we want to satisfy, then if we want our Q to remain at 1 and Q bar to remain at 0, the voltage this Vx or this VQ bar is kind of applied to input of this inverter 2. So this voltage Vx should not be greater than the Vm of inverter 2. Since we are talking about matched pair of inverters, so we have Vm of inverter 2 equals to Vm of inverter 1. But the condition for non-destructive read, I would say, that is the SRAM cell content is not flipped. For that, the condition is just that Vx should be less than Vm of inverter 2. And we also saw that to satisfy this criterion, what we should have is, we should have the strength of this NMOS transistors of inverter 1 and 2, basically, since they are kind of matched inverters, the strength of this NMOS transistor should be greater than the strength of the access transistor, right? This was the criterion that we had if we wanted our Vx or the node potential at VQ bar during the read operation to be as low as possible. We wanted to have a pulling strength of NMOS towards ground as high as compared to the access transistor full strength. So this was the condition during the read operation. This was the kind of constraint on the sizing of your NMOS of the inverters with respect to the access transistors. Now let us look at the right operation. So let us look at the right operation. Let me draw the circuit diagram for the right operation similar to what I have drawn for the read operation. So during right operation also we have this M5, then we have this cross coupled inverter pair. This is inverter 1. This is inverter 2. This is M6. Okay. So then we have this VBL, we have this VBL bar. And let us take the same case that our Q is equals to 1 and Q bar equals to 0. Now we're told that since we have, now if you want to flip the state of this SRAM cell, what we'll have to do is we'll have to apply VBL equals to 0 and VBL bar equals to 1. Now that we have already sized our inverter, like NMOS and access transistor in such a way that this VQ bar cannot go beyond this BM of inverter 2, we cannot flip the contents from left side. So we cannot flip the content from left. How can we flip the contents? We have to size our other like the pull-up M4 and the access transistor so that we are able to flip it from the right. So how do we flip it from the right? So on the right hand side, if you look at this, so you have this PMOS of inverter 2. So you have this PMOS of inverter 2 pulling this node VQ towards VDD. And you have this access transistor M6 pulling this VQ bar or pulling this VQ towards ground. So here also there is a tug of war between the PMOS of inverter 2 and the access transistor M6. Whoever wins or whoever pulling strength is larger will kind of pull the potential at this VQ towards ground or towards VDD. Now in order to flip the content of this bit cell, what we ideally want is this VQ is kind of your input to inverter 1. Now this VQ is kind of input to your inverter of 1, right? And you want the output of the inverter 1 to flip from 0 to 1. So what ensures that your output is actually flipping from 0 to 1? If the input to your inverter kind of goes below its VM value, you are sure that it's kind of switching from 0 to 1. So we want our VQ to be less than VM of inverter 1 for right. And what was the criterion to ensure this? The criterion was we had to make our PMOS of inverter 2 or the pull strength of PMOS of inverter 2 lesser than the pull strength of access transistor of the SRAM cell. Now we discussed that what happens is usually we design our inverters such that the pull strength of NMOS is same as the pull strength of PMOS. Why so? So there are many conditions. First, symmetric PPLH, PPHL. Then we also cared about noise margins. So the noise margin should be as high as possible, and because of that, also you want your strength of NMOS to be equal to the strength of PMOS. However, here we get stuck with two different conditions. First, for read, your access transistor has to be less powerful as compared to your NMOS, inverter NMOS. And for write, your access transistor has to be more powerful. than your PMOS. Usually, the strength of your NMOS and PMOS in any inverter is kept same. So your NMOS strength is equal to your PMOS strength. For read, you want your access transistors to be less powerful. For write, you want your access transistor to be more powerful. So it's kind of, a conflicting constraint. So this is known as read-write conflict. And what people generally do is, how they size their SRAM, how they size the transistors in SRAM is, you have the strength of your PMOS is least. Your strength of access transistor is kind of higher than your PMOS. And your NMOS of the inverters is kept most powerful. However, this leads to asymmetric design of inverters in a SRAM cell. Now, there have been similar, like apart from this 60, there are also multiple SRAM cell designs, and one of them I discussed in the last class, that was 80 SRAM cell. So in 80 SRAM cell, you had decoupled read and write paths. So because the read and write paths were decoupled, you didn't have any size constraint. So there was no size constraint for read or write operation. However, the disadvantage there was, since you had 2 bit lines for write and 1 bit line for read, so you total had 3 bit lines compared to 2 bit lines in a single SRAM cell, and you also had 2 word lines, one for read and one for write. So it was like one was read word line and one was write word line. So you had 2 word lines, one for read, one for write, as compared to one write, like one word line for your single S60 SRAM cell. So because of this, routing complexity was there. How you are going to route these many word lines or bit lines in your large SRAM cell, large SRAM array design. So routing complexity was there. And also, since you have increased your transistor count from 6 to 8, you also had this density constraint. So I've been telling this time and again, in your examination, you may see a question where you'll see a different flavor of SRAM, maybe 10T SRAM cell or 11T SRAM cell or whatever. And then you may be asked, what could be the potential benefits of this structure and what could be the potential demerits of this structure? So you have to think along these lines. Think about density, think about routing complexity, think about write operation, read operation. The steps remain same in the read and write operation. You think about them and think about what exactly can be a problem with this kind of cell. What exactly could be the advantage of this cell? So you think along those lines, and then you'll be able to answer these questions very easily. Now with this recap, let us go ahead and look what exactly is the hold static noise margin, or what exactly are the noise margins in your 60 SRAM cell. So apart from read and write operation, there is also some operation which is known as hold operation. So as the name suggests, in the hold operation, you just have to retain the data value which was stored in your cross coupled inverter pair. So in your hold, the condition on word line and bit line is you assert word line as 0. You also keep your bit line to 0. So the kind of circuitry that you end up with during this is, you end up with this itself. You have this inverter 1, you have this inverter 2, you have this node as Q, you have this node as Q bar. If let's say Q was 1, it has to remain at 1. If Q bar was 0, it has to remain at 0. So this is the kind of circuit that you end up with when you have word line is 0 and bit line is 0. Now let us look at what exactly is the static noise that we are talking about. So let us look at the static noise. So static noise can be any DC offset. It can be any noise introduced by the power supply. Or it can be because of thermal noise. So if you just talk about thermal noise, the average value of this thermal noise, if we represent it as Vn, so the average value of any noise will go to 0, because there are variation is equally on both sides, and the polarity is equal on both sides. If you take a long-term average, so that way its average value goes to 0. So what we talk here for noise is their RMS value. So how we represent the RMS value of your thermal noise is Vrms square is equal to 4 kT RDF, where frequency f1 to f2 is kind of your bandwidth or whatever range of frequencies you are considering. So Vn is nothing, or Vn RMS is nothing, but it's the root of 4 kT R bandwidth. So this is you kind of define your Vn for your thermal noise. Now, how exactly this static noise play a role in the operation of this SRAM cell in hold is, you can have these static noise sources. You can have these static noise sources adding to the input or output of these two cross-coupled pairs. And when they kind of add or they kind of superimpose themselves on these input-output pairs, they may lead to flipping of your already stored data. So this whole static noise margin kind of gives you the maximum value of the static noise that can be applied to this inputs and outputs of this cross-coupled inverters, so that the cell content is not flipped. So that is how you define your HSNM. So this is called HSNM, and how you define it is, for the worst case polarity, we'll define it in a minute. What exactly is the worst case polarity? So for the worst case polarity, which kind of leads to your positive feedback and flipping of your this existing state of this SRAM cell. So for the worst case polarity, maximum static noise that your cross-coupled inverter or bistable element can sustain without flipping the states. This is your whole static noise margin. So now with this definition, first what we need to do is we need to find this worst case polarity. So let us look at our kind of this bistable element with these noise sources appended. So let us take the first case. Let me just draw the inverters. Let me use a different color, as you guys told me. So let us have a noise over here. Let us have a noise over here. Present this by Vn, present this by Vn as well. Let us connect these together. So this node was Q equals to 1, and let us say that this was Q bar equals to 0. So let us take this polarity as negative, and let us also take this polarity as negative. So by negative polarity, I mean you attach negative terminal of this noise source to the input of your SRAM or input of your inverters. So now in this case, let us look at the VTC of inverter 1 and inverter 2. Let us call this inverter 1 and inverter 2. So first let us draw the VTC of inverter 1 over here. Let us say this is inverter 1 VTC, and let us draw the VTC of inverter 2. Let us call this VTC of inverter 2. So let us draw it without, like, in the absence of noise. Okay. So now when Q is 1, when the effective input that this inverter 1 sees. Earlier it was VDD, since your Q was 1. Now the effective input that inverter 1 sees is VDD minus Vn. Let us say this is our Vn. It's actually very small, but here I am drawing it large so that you get a feel of what is exactly going to happen. So for this input, which is VDD minus Vn, what happens is the output changes from 0 to this appreciable value. So let's call this output as Vx. So now at the output of 1, you have a potential which is Vx. So now this Vx is kind of your input to 2. Earlier your input to inverter 2 was 0. Now your output is Vx. Sorry, now your input is Vx to this 2. And on top of that, you are subtracting this Vn, right? Because your negative terminal is connected to the input. So effective voltage that is coming at the input is Vx minus Vn. So you increased your input to Vx because of this noise source. But now that is kind of reduced by this Vn because of this polarity. Because we had a polarity in which the negative terminal was connected to 2. So instead of Vx, now we come back and we apply Vx minus Vn. So we apply this input. And because of this, your output still remains close to VDD. So this node potential, the output of this 2 remains close to VDD. So this Vx was kind of reduced by this Vn because of this polarity. So any increase that was being done by this noise was kind of being compensated by this noise, so that the system remains at the same state more or less. So this is not the worst case. So what would be the worst case? Let us just flip the polarity of the second bit also, so that it leads to a positive feedback. So let me draw that case. So here what we do is, you again draw the same thing. Now we draw the noise sources with opposite polarity. Opposite polarity for only the second one. Let me draw this and then it will become pretty clear. Okay. So now with this, let us keep the polarity of this same, because it was kind of flipping the bits in the other direction. But here, instead of having minus and plus, we use plus and minus. Now let us call this as q bar equals to 0 and q equals to 1. Now let us try to understand it from the VTC of 1 and 2. So now let me use a different ink for 1 and 2. So let us draw the VTC of inverter 1 and inverter 2. Let us draw the VTC of the two inverters. So we have, let's say, this as the VTC of inverter 1. Let us say this is the VTC of inverter 2. So earlier, the input to inverter 1 was Q equals to 1, which is VDD. So the input was this. So the output was close to 0. Right? Now, the input effectively is VDD minus Vn. So we shifted this input by this Vn. Let's call this as Vn. So we shifted this input by this Vn. And let us say that we reach this output, which we call it Vx, let's say. So now we have this Vx, which will be here. And now this Vx is kind of the input to this inverter of 2. So earlier your input to inverter 2 was 0 because your Q bar was 0. So your input was 0. Now it will be Vx, and on top of that, you're also adding this noise source. So because of this noise, the input to inverter 2 is Vx. And on top of that, you're also adding this Vn. So you're also adding this Vn. So the effective input to inverter 2 is this. And the corresponding output now becomes close to 0, right? This becomes some value Vy, which is close to 0. So the output is Vy, which is very close to 0. Now if this Vy is kind of again applied as the input to 1, let's say this Vy, which is close to 0, is applied as input to 1, and that is because of this addition of this noise source at the input of 2. So because of this Vy, what will happen is this effective voltage is further reduced by Vn. So the effective voltage that goes to 1 is Vy minus Vn. So that becomes close to this 0, and the output that you get is 1. So here what happens is the effective voltage that this inverter sees is close to 0, and its output becomes close to 1. So you started with Q equals to 1 and Q bar equals to 0, but because of this positive feedback that these noise sources are providing, I mean the positive feedback is because your inverters are running in a cross-coupling configuration, but because these noise sources polarity are in such a way that effectively you are able to flip the content of the cell. So you started with Q equals to 1 and Q bar equals to 0, but because of this introduction of two noise sources with different polarities, what you end up with is that your Q becomes 0 and your Q bar becomes 1. So that is what happens when you have a very large noise source or very large static noise in your circuit. So now let's look at how people measure this whole static noise margin. So for measurement of this whole static noise margin, what people do is, let us say this is our structure. So this is inverter 1, this is inverter 2, so this is 1, this is 2. What people generally do is they kind of take the VTC of these, 1 and 2. So let us say that I use different colors for VTC of 1 and 2. Let's say this is VTC of 1. So we represent this VTC as blue, and we present the VTC of second by red. And how we do that? I mean, we draw it on the same axis, since your input to this 2 is kind of output of 1 and vice versa. So what we do is we draw it on the same axis and we get something like this. So this is the VTC curve of bistable element basically. And here what we have done is we kind of draw the VTC of 1 with blue, 2 with this red. And then what people do is they try to fit in a square with maximum side inside this lobe. So what they do is they try to fit a square inside this lobe, and then they try to find the maximum size of this square, or the maximum size of the diagonal, because any square whose diagonal is maximum will have the maximum sides. And then they call this side of the maximum square that can be fitted in these lobes as Vn. So you have two lobes, and the size of the maximum square that can fit inside those lobes is called Vn. And then this Vn is your whole static noise margin. Now a question arises, why does that even make sense? Why do we fit in a square, and how does that even make sense? Okay, so let me answer that question. So now let us draw the circuit with noise present here. So now let us draw the circuit as we have drawn for the worst case polarity. So we know that for the worst case polarity, how it looks like is we have this noise source over here, which is kind of connected to the polarity is like this. Then here we have again a noise source, and we have this inverter 2. And here the polarity is opposite. That is, the positive terminal is connected to the second inverter's input. So we have this kind of configuration in the worst case for HSNM. To understand this, let us draw the VTC of inverter 1 and inverter 2 in the presence of noise. So what that means is basically apply an input over here and check the output over here for inverter 1. And for inverter 2, what we do is we apply an input here and check the output here. This is how we draw the VTC in the presence of noise. So what we do, or what we know from our discussion in the previous lecture, if we have this negative terminal of noise connected to this inverter 1, the effective input to this is V in minus Vn, and hence the curve shifts towards right, if you remember. And for the other case, the effective input to inverter 2 is V in plus Vn, so the curve shifts towards left. Now let us apply the same concepts over here. So for inverter 1, what we have to do is, if Vn is the noise, or if Vn is the maximum noise that can be applied, let us shift this towards right by Vn. Let us say this is Vn. So we shift it towards right by this amount Vn. And now, for the other one, I mean for VTC of inverter 2, let us also shift that by Vn towards left. So what does left here means? Left here means towards bottom right. So let us shift it towards the bottom. So if you shift these curves, so what exactly the intersection of these curves give us? So if you had any bistable element like this, the kind of characteristics that you got was a butterfly curve in which you had this 3 points of intersection. We called A and B as stable states and C as metastable states, because in the presence of any noise, it will trip to either of the 2 states, that is A and B. But once you are actually applying this Vn with such a polarity, what is happening to your VTC of these systems? I mean, what is happening to your intersection points? It is now limited to only 2 points. So you have one intersection point here, one intersection point over here. So from 3 intersection points, now you have got only 2 intersection points. Now let us summarize whatever we have discussed. So what we discussed was, if the shift in the characteristics, if the shift, let's call that V shift in the characteristics because of noise is less than or equal to your HSNM. What is your HSNM? The maximum side of the square that can be fitted in this in these 2 lobes. If that is kind of, if we are calling that as Vn, and if your V shift is less than or equal to Vn, then what we have is, we still have 2 intersection points. Now what happens if we increase our V shift beyond this value of HSNM or Vm? That is the maximum size of this square. You would be left with only 1 intersection point. And that intersection point will be the flipped state. And that is something that you don't want. You want your cross-coupled pair to hold the data without flipping, right? So this is the importance of this hold static noise margin, and how people measure it. They kind of just do this VTC. They draw this cross-coupled inverter characteristics, and then they try to fit in the size of maximum square that fits in here. Kind of gives you your hold static noise margin. What happens if you exceed the value? Like, what happens if the noise in your circuit is larger than this hold static noise margin? You kind of end up in the flipped state. So this is how we define your hold static noise margin. Discussion on hold static noise margin. Let us move to another important performance metric for your SRAM cell, which is read static noise margin. So read static noise margin is kind of the maximum noise. So how we define this read static noise margin? So it's the maximum value of static noise that your SRAM cell can tolerate without flipping the states when it is in read mode. So what is the effective circuitry when it is in the read mode? So let us draw that. So you have this, let's call this bitline bar. This is P-charge to VDD. We have this access transistor M5. Then we have this cross-coupled inverter here, right? So we have this inverter 1. We have this inverter 2. And then you have M6, which is the another access transistor, and then you have bitline. And you have this as also P-charge to VDD. And we are taking the case when your Q node was pre-charged to 1. No, sorry, not pre-charged. Q node is storing 1 and Q bar is storing 0. So this was the case that we were discussing. Anyways, so how do we measure this read static noise margin? So how we measure this read static noise margin is, again, we draw VTC of inverter 1 and VTC of inverter 2. How we draw it? So for this, what we do is, in this read condition, for let's say inverter 1, what we'll do is, for inverter 1, we'll sweep the voltage at Q and check the output at Q bar. Similarly, for inverter 2, what we'll do is, we'll sweep the voltage at Q bar, which is its input, and check the output at node Q. So this is how we kind of measure, this is how we first draw the VTC of inverter 1 and inverter 2 on the same kind of axis. And then again, we try to fit in the maximum square inside those loops. So first, let us draw the VTC of this inverter 1 and inverter 2 in the read mode. So how exactly does this configuration look like? Let us take the case of inverter 1 first. So let us look at inverter 1. So for inverter 1, this is, this is the case. This is inverter 1. You have this node as Q, where you are sweeping the voltages. And at the output of this, what you exactly have is, you have this M5, which is connected to VDD. So let us simplify this. So now if we simplify this, what we get is something like this. This is Q, right? Then we have this potential. This is M5. This is VDD. This potential we are calling it Q bar. Let's call that Q bar. This is VDD. And let us say this is out. Now let us attempt to draw its VTC. So let us make a curve over here. Let us try to draw its VTC. Okay. Now let us take the case when your VQ is 0. This is its input and it's Q, let's say. Let us take the case when your VQ is 0. When your VQ is 0, this NMOS is turned off and your PMOS is turned on. So this Q bar will be charged to VDD through this PMOS, and also since this VDD is already connected to this Q bar through M5, so both of these will try to charge this node VQ bar to VDD. So we start with this VQ bar as VDD. So if you say this is VQ bar on this axis, this is VQ on this axis. So for VQ goes to 0, VQ bar is VDD. So we start with this. Now what happens when your VQ bar or when your VQ is VDD? So when your VQ is VDD, what happens is your PMOS turns off. However, your NMOS turns on. This is your M1. So your M1 turns on, right? Now, once your NMOS turns on, this kind of, this load capacitor over here, which was CVL bar, kind of discharges through this M1. And because of this Q bar is actually fixed at some voltage, which is pretty less than VM of inverter 2, but it is greater than 0, and let's call this voltage as Vx, right? So basically, this starts behaving like a resistor divider circuit. So you have VDD applied to resistance of M5 and M1 in series. So the voltage at the intermediate node, because of this resistance divider configuration, we are calling it Vx. So when VQ is VDD, you have the output, that is VQ bar as Vx. So this is Vx. And in between, it will look something like this. So this is how your VTC will look like in the read configuration for inverter 1. Similarly, if you look at inverter 2, let us take the case of inverter 2. So for inverter 2, you have Q bar as the input. So you have something like this. This is your Q bar. And then you have, this connected to M6. And this is again connected to VDD. This is VDD. This is top. So let us draw it on the same scale. So let us use black color, or let's say red color for this VTC. So now what happens when VQ bar is 0? Again, this node VQ will be charged to VDD, right? Because both of these PMOS and this M6 will try to charge this node, and this NMOS is turned off at this time. So when VQ bar is 0, that is at this point, what exactly is your value of VQ? That is VDD. So you start with here itself. This is your VQ. When your VQ bar is 0. Now what happens when VQ bar is VDD? So when VQ bar is VDD, this turns on, this turns off. And again, the same thing happens, that is, this kind of, discharges this load capacitor which was there, and this load capacitor is CBL. And because of this resistance divider configuration, you have VQ placed at some voltage, which is Vx here also, because we are talking about matched inverter pairs. So here also you have Vx. So when your VQ bar is VDD, what happens to your VQ? VQ is some value which is Vx. So if you draw its VTC, it will also look something like this. It will look something like this. So now you see what would be this noise margin, or the read static noise margin. As we told, it would be the size of the maximum square that can be fitted inside, like this. So you see that the size of the maximum square has reduced considerably as compared to the case where we had this, hold static noise margin. Just because of the presence of these access transistors and this VDD, your VTC shifts now. I won't call this a shift, but it kind of gets distorted. And because of this distortion in the VTC, what exactly happens is you can see that the size of the maximum square gets reduced, and as such, your RSNM gets reduced as compared to your HSNM. Now on the same curve, if we were to plot your VTC without any noise or without anything, so it will look something like this. So we'll have something like this. We'll have this going like this, and we have this. On the same curve, if you plot it, so you will see that the size of the maximum square is kind of larger as compared to the size of maximum square that we have in the read operation. So what does this imply? So this first implies that your RSNM is less than your HSNM. So your RSNM is less than your HSNM. What does that mean? Your read process is more sensitive to noise. Now, what is happening in this modern day SRAM is their scaling is kind of limited because of first static leakage that I discussed, and second, low read noise margin. Why the read noise margin is low? Because the read noise margin is already very low as compared to your whole static noise margin. And in these future technology nodes, you are kind of also scaling up your VDD. So now your VTCs would be scaled up something like this. So if you scale your VDD, you're also scaling up the maximum size of square that you can actually induce inside it. So this reduction in VDD, your static noise margin is also reducing. So if the magnitude of your noise is larger than this read static noise margin, then your SRAM will cease to operate. I mean, every time you read it, your bit will flip. Scaling of technology node, what is happening is exactly your noise to signal ratio, that is VNN to VDD, it's kind of getting high, right? And because of that, your SRAM cells are becoming more sensitive to noise. Okay, so with this discussion on read static noise margin, let us look at the writability of SRAM. What exactly is the writability and how we measure it? So what exactly is writability? It's kind of, it tells you the ease of writing to your SRAM cell. Ease of writing data in your SRAM cell. Now, what do you mean by ease of writing data? So it can relate to, if the data or if your bits can flip at a very low value of VPL applied, then it also means that, you can write your data in your SRAM cell very easily. So for this, let us first draw the circuit of this SRAM cell in the write mode. So I'll be using the same kind of configuration. So I'll be using this kind of configuration where you have this access transistors, you have this BL bar, you have this M5 access transistor, then you have this inverter 1, you have this inverter 2, you have this M6, then you have this DL, right? Let us say that we have this Q equals to 0 and Q bar equals to 1. Let us say we have this configuration where Q is 0 and Q bar equals to 1, which is already stored. And now what we want to do is, we want to flip the content of this cell to a value which is Q equals to 1 and Q bar equals to 0. So for this, what we do is, we apply VBL equals to VDD and VBL bar equals to ground. This is what we do in general. But here, to measure this, to measure the writability of our SRAM cell, what we'll do is, we'll keep our VBL bar to ground, but we won't apply a VDD to VBL. What we'll instead apply is a RAM, a DC RAM. So if this is VBL and this is time, we'll apply a DC RAM like this to this VBL, to this BL terminal, and then we'll see the outputs at Q and Q bar. So let us look at how this looks like and how the timing diagram looks like when you're applying a RAM. So let us draw a timing diagram. So let us have something like this. So the x-axis is kind of time. This is your voltage. Okay. And then this is your VBL. Now, as your VBL is increasing, as this VBL is increasing, your Q and Q bar potentials will also change. So when this VBL increases, then it also tries to, pull this Q towards VDD. So now let us draw Q and Q bar on the same axis. How those change. So let us say for SRAM instance 1. So let us say we have two SRAMs. For first SRAM, we have the Q and Q bar characteristics like this. So initially your Q was 0, so it's here. This is your Q equals to 0 initially, and your Q bar equals to 1. So this is at VDD. Let us draw this VDD like this. Now let us look at how basically this Q and Q bar are behaving as you are ramping up your bitline voltage. So this Q equals to 0. So this Q will try to go towards 1. So let us say, as your VBL increases, this Q kind of starts like this and then it tries to go towards 1. And let's say it reaches 1 there. Similarly, for Q bar also, it will start at 1. However, at some point of time, it will try to flip towards 0. So this voltage is of utmost importance to us. Why? Because at this, we have VQ equals to VQ bar, right? And what would be that value? That would be equals to VM of the VM of these inverters. So why this is important? Because if we somehow reach this value, if we somehow reach this condition, VQ equals to VQ bar equals to VM, we are sure that bit content will flip. Now, how we define this writability? So what we do is, we kind of, at the same instance, wherever your VQ and VQ bar collide, I mean, wherever you reach this VQ equals to VQ bar, at that time instance, we kind of look at the difference between VDD and your bitline voltage. So you define this right noise margin or writability as VDD minus the value of VBL at location where VQ equals to VQ bar. Now, how does this give you an idea about writing ability or how easy it is to write in this SRAM cell? To understand that, let us take the case of a second inverter. This was for the case of SRAM 1, let us say. Let us take the case of SRAM 2, which is another SRAM which has been designed by in some other process technology node or with some other specs. So what we observe for SRAM 2 is, there also we stored Q equals to 0 and Q equals to 1. But as we ramped our VBL, it changed like this. So here, if you look at this trip point, so this point where your VQ equals to VQ bar equals to VM is also called, trip point. This is also called trip point. Why trip point? Just because if we have reached somehow at this point, we are sure that the content will definitely flip. Now, if you kind of look at the difference between this VDD and the bitline voltage at this point, I mean, if you look at this magnitude, which is we define as right noise margin of the second SRAM cell. So if you look at this, you'll observe that right noise margin of second SRAM cell is greater than right noise margin of first SRAM cell, right? What this means is your ease of writing to 2 is greater than ease of writing to 1. How this is implied by this diagram? So this diagram simply means that the bitline voltage for which you are able to kind of flip the data of inverter 2 is smaller as compared to the bitline voltage for which you are able to flip the contents of cell 1. So if a lower amount of bitline voltage is needed to flip the contents of 2 as compared to 1, it is definitely easy to write to 2 as compared to writing to 1. And you can also have some cases which can be called as extreme cases, but in those cases, what you'll have is you'll have this Q bar going like this, and you'll have this Q going like this. So even when your VBL reaches VDD, the Q and Q bar don't intersect. So we don't have this VQ equals to VQ bar ever, even when VBL reaches your VDD. So for those cells, we'll say that there is a write failure. So we won't be able to write to those SRAM cells. So this is how we define the writability. There are other ways of defining write noise margin as well, but nowadays this is the most common used method. But to define everything, I mean to define the writability, the hold noise static noise margin, or the read static noise margin, you need to somehow access these internal nodes. You need to access these internal nodes, and you kind of need to probe them with some voltage or some. You need to apply some voltage at this node and check the output here. However, these nodes, if you want to probe them in circuits, what you'll have to do is you'll have to kind of provide additional interconnects. additional pins on the chip, which you can access through which you can access these two terminals. But that is not possible in commercial SRAMs, which are like very large, which are very huge. Nowadays, industries have come up with several new techniques like WRRV and different other techniques, which I shall be giving you an assignment to learn about them, in which we don't have to invade, or that is known as non-invasive kind of measurement technique, where we don't need access to this Q and Q bar. In general, what we have access to is your bitline bar, and word line, which is here. If you can do the measurements using that only, it would be great. If you can measure all the performance metrics of the SRAM using those three terminals itself, it would be great. Okay, so with this, we kind of end our discussion on the noise margin of your SRAMs.